Welcome back. From the previous videos, you know that every node on the Bitcoin network forms a candidate block for the blockchain and competes with the other nodes on the network to get their block onto the blockchain through a process called mining. It was explained that the header of any candidate block has certain fields that can be changed without affecting the function of the block. To mine a block, a node must find values for the changeable fields in the header such that a hash of the block header results in a number that is smaller than a target number. How is this target number for mining established? The Bitcoin system was developed with the goal of having a new block successfully mined about once every 10 minutes. Why once every 10 minutes? This was largely because the creator of Bitcoin wanted to give time for a mined block to propagate through the network and be added to the copy of the blockchain in each of the nodes in the network before a next block was mined and competing to be added. The system controls the rate of successful mining of new blocks by controlling the target number. The very first target number was simply a guess by the creator of Bitcoin of a target hard enough to meet that it would take on average about 10 minutes for some node in the network to succeed. In order to keep the rate of addition of blocks to about 1 every 10 minutes, the target is recalculated by every node after the addition of every 2016 blocks to the blockchain. Each node maintains the same target number because the first target number and the formula for updating the target number are hard-coded into the Bitcoin system, and because the header of each block also includes a timestamp to record the approximate time that the block was added to the blockchain. Each block added to the blockchain is given a block number, and once a node notes that a block has been added to the blockchain with a block number which is a multiple of 2016, the timestamp of the newly added block is compared with the timestamp of the block 2016 blocks earlier to determine an elapsed time. From this, an average time to add a block is calculated. If the average time is more than 10 minutes, the current target is relaxed to make it easier to mine a block. But if the average time is less than 10 minutes, the current target is tightened to make it harder to mine a block. In this way, the average time to mine a block can be maintained close to the goal of 10 minutes. The target at the time a block was added to the blockchain is another field in the header of the block. So to mine its candidate block, a node changes one of the changeable fields in the block header, hashes the data in the block header, and sees if the output of the hash is a number less than the target value. Well, what fields in the header can be changed? The primary field that can be changed is the nonce, which means number used once. The nonce is only used for mining. A node can pick a value for the nonce, take a hash of the block header, and compare the result with the target. If the hash is greater than the target value, the node tries again with a different value for the nonce, and so on. There's an issue though. The nonce field is only 32 bits long, which limits the number of possible nonce values. What if a node tries all possible nonce values and still has not found a hash value less than the target value? In fact, this is what usually happens. Now what? Fortunately for the node, the nonce is not the only field in the header that can be changed without invalidating its candidate block. The timestamp can also be changed, at least to some extent. This is because the Bitcoin system will accept any timestamp value in a block which is within a certain range of the system time. The node could, therefore, adjust the timestamp by, say, 1 second, and again find a hash of the block header. If the hash value is still too high, guess what? The node could run through every nonce value again with a new timestamp to get further hash values. And if none of those work, the node can adjust the timestamp again and again run through all the nonce numbers with this further timestamp. Okay, well, what if the node runs through all permissible adjustments of the timestamp, and for each permissible timestamp runs through all the nonce values, but still has not found a magic combination that hashes the header data of the block to a value less than the target. Can the node do anything else? The node obviously cannot change the pointer to the prior block in the header, and it cannot change the target value. There are two further fields in the block header to consider. The first is a version code. This field is included because occasionally there's an upgrade of the Bitcoin system, and the version code specifies which version the block follows. But the version is the version. It's not a field the node can adjust. This leaves just one more header field, the Merkle root. That's a scary name. What is it? The Merkle root acts as a fingerprint for all of the transaction records in the block. It's calculated by taking hashes of combinations of transaction records in the block, then hashing combinations of these hashes, and so on until a single number is obtained, which number is the Merkle root. After calculation of the Merkle root, if any transaction record inside the block is changed in any way, the transaction records of the block will generate a different Merkle root. So the Merkle root flags any problems with the block data. Okay. Obviously, we cannot change the Merkle root, as that will indicate there are problems with the block data, right? True, but the node can use a little trick. Remember that the first transaction record in every block is a Coinbase transaction record. The Coinbase transaction record has the same fields as any other transaction record, but some of the fields in the Coinbase transaction record are not used for anything. What this means is that the node is free to adjust those fields without affecting anything. And if the node does that, what happens? Well, it changes the Merkle root in the block header, which in turn changes the hash value of the header. So by inserting values in unused fields of the Coinbase transaction, the node can get many more hash values, cycling through the nonce values and the timestamp values for each new Merkle root. Indeed, if the node gets desperate, it can even reduce the amount of Bitcoin in the Coinbase transaction record that it would be entitled to if it successfully mined the block to calculate yet further hash values. This works because other nodes would be happy to validate a block where the successful node takes less Bitcoin than it is entitled to. They would only refuse to validate the block where the node tried to take more than its entitlement. The order I've described for changing the changeable fields in the block header is only by way of example. The node is free to change the changeable fields in the block header in any order it wishes. The only rule is that it find a header hashing to a value lower than the target. Eventually, one of the nodes will successfully mine its candidate block by finding a hash of the header data of the block that is lower than the target. Let's say it is node A that successfully mines its candidate block, block A. Node A then puts block A on top of its local copy of the blockchain and transmits block A to other nodes in the network. As soon as another node, say node B, receives the mined block A and validates it, it puts it on top of its own copy of the blockchain and also passes block A on to further nodes. Node B then updates its mempool and UTXO databases, discards its candidate block B, and immediately begins working on creating a new candidate block, hoping for better luck mining with the next block. Well, that's what node B is supposed to do according to the rules. But what if node B decides not to follow the rules? Let's say node B, after receiving block A, does not put block A on its local copy of the blockchain, does not pass block A onward to other nodes, and does not discard its candidate block B. Instead, node B keeps working on its own current candidate block, block B. B's plan is to succeed in mining its block B and then pass block B to other nodes rather than passing along block A. In this way, node B hopes to steal the block subsidy. Sneaky node B. The problem for node B, though, is that most or all of the other nodes in the network will follow the rules. This means about 500,000 nodes will have put block A on their copy of the blockchain and be trying to mine their next candidate block, while node B chugs away trying to mine its current candidate block. Odds are heavily in favor of one of the 500,000 nodes successfully mining its next block before node B has mined block B. When that happens, the next successfully mined block, that we'll call block N, gets passed around and added to the blockchain. But node B is determined. It won't add node N either. It will keep on trying to mine block B. Indeed, several more blocks may be added to the blockchain before node B eventually successfully mines its block B. When node B finally does successfully mine block B, it delightedly passes it to other nodes. The other nodes will verify block B was successfully mined, but they note a problem. A new block to be added to the blockchain is supposed to point to the block at the top of the blockchain. The other nodes will see that block B instead points to a block that is now buried in the blockchain. So these other nodes will set block B to the side and not put it on the blockchain. In the result, node B has wasted its time. Node B would have been better off if it had just followed the rules, accepted it lost the race to mine a block, put block A on top of its blockchain, discarded its candidate block B, and got on with trying to mine a new candidate block. But this does beg a question. What if a node, say node A, mines its candidate block A, and at about the same time, a node B mines its candidate block B? If this happens, both nodes will add their own block to the top of their local copy of the blockchain at about the same time, and send their own block out to the other nodes to add to the local copies of the blockchain in the other nodes. The result will be that the nodes which happen to receive block A first will add block A to the top of their local copy of the blockchain, and the nodes that happen to receive block B first will add block B to the top of their local copy of the blockchain. Further, when a node having block A on top, like node D in the diagram, eventually receives block B, it will see that block B was successfully mined, but that it does not point to block A as the immediately preceding block in the blockchain, but instead to the block under block A, block Z in the diagram. Therefore, each node with block A on top will not add block B to its local copy of the blockchain, but will keep block B off to the side. For the same reasons, each node with block B on top, such as node E in the diagram, on receiving block A, will not add block A to its local copy of the blockchain, but will keep block A off to the side. Now we have a problem. There are two different versions of the blockchain in the network. How does this get resolved? It gets resolved when a next block is successfully mined. Recall that as soon as a node adds a block from another node onto the top of its local copy of the blockchain, it discards its own candidate block and begins work on a new candidate block to go on top of the new top block. So let's say node D creates a new candidate block D and tries to mine it on top of block A. Let's also say node D is lucky and succeeds in mining block D very quickly. As soon as it does that, node D puts block D on top of block A in its local copy of the blockchain and sends block D off to other nodes. When node E receives block D, it sees a problem. Node E had put block B on top of its local copy of the blockchain and set block A off to the side. But now it has received a successfully mined block that goes on top of block A. A rule of the Bitcoin system is that each node adopts the longest version of the blockchain as the correct blockchain. Here, node E realizes that a blockchain topped with blocks A and D is longer than a blockchain topped only with block B. Consequently, node E reorganizes its local copy of the blockchain to remove block B, from the top of its local copy of the blockchain and replace it with blocks A and D. This approach will result in the re-establishment of a single version of the blockchain across all nodes. If you have watched the videos of this series, you should now have a good understanding of how the Bitcoin system actually works. It's an impressive system and has led the way to the creation of many other cryptocurrencies. Subscribe to this channel to learn of future videos explaining other technologies.